Hi everyone, I'm David McAuliffe, and my project is all about kitchen sponges, and more specifically how temperature affects how much water that they can absorb. The kitchen sponges are doing the absorbing. The temperature is the independent variable that affects the dependent variable, the water. My defining question was, how does temperature affect the absorption capacity of a kitchen sponge? And my hypothesis was that if the temperature rises, the absorption capacity, or the amount that the sponge can absorb in milliliters of water, goes down. This is because of pores, water density, and surface tension. Pores are the little holes in the sponge that actually allows it to absorb the water. Water density is how much of a certain amount of water is in a certain amount of volume. And if the temperature of that water rises, its density lowers, which in turn makes its volume go up, which means that the sponge would be able to absorb less of it. Surface tension is the force at the surface of a pile or cup or any space of water that keeps the water together, and that force lowers as the temperature rises, so therefore the water would fall out of the sponge more readily because there isn't any surface tension holding it in anymore at higher temperatures. And this is all in order to improve our cleaning by making it more efficient to see what temperature of water is actually the best. My abridged procedure to test this is to pour water on sponges to saturate them, and once the water falls beneath into the plate shown in the top right corner, that's when that trial is done. First, heat or cool or let the water sit for your desired temperature, room temperature 40 degrees or 140 degrees Fahrenheit. Second, pour the then measured water, that is in a measuring cup now, using a baster on top of the sponge, and stop once water drops out, and then record what is left. And then you subtract that from the original 1 cup value, and that's how much water the sponge absorbed for that one trial. My results were that 140 degrees absorbed the least and 40 degrees absorbed the most, and what was interesting was that there was a far greater gap between the 68 and 40 degrees rather than the 140 and 68 degrees. The t-test values were very low, so both were significant. Both are nearly assuredly completely dependent on the temperature. But between 40 and 68 was more significant as the t-test was lower. So as heat went up, absorption went down, and as heat went down, absorption went up. The graph displays these findings and shows little room for outliers. The conclusion is that the hypothesis is supported. In order to go further with this, we could create an equation that shows by what exact number the water absorbed goes up with a lower temperature, and when it changes and when it stops. We could test different liquids and different porous materials, like, for instance, piles of gravel, piles of sand, and other things that aren't just piles of small rocks, like a piece of super porous wood or dry wood, and different liquids for different scenarios, such as blood on a crime scene, and other liquids as well. And a further exploration could be going into why that the gap between 60 and 48 degrees was so much wider than 140 and 68 degrees. And here we have an example of an equation, almost completely not correct, but that could just be an example. And that is the conclusion to my presentation. I hope everyone enjoyed it.